In this video, we'll be discussing simple harmonic motion representation and analysis. So let's start off with the position as a function of time. So we have x of t is equal to a amplitude times cosine angular frequency t plus the phase shift, or x of t, a sine of omega t plus the phase shift. And we have t there as well. So what we realize is that simple harmonic motion, it varies sinusoidally, not linearly. And also we can take the derivative of the position. So this is that's the derivative of the position. So that is v of t is equal to negative a omega sine omega t plus the phase shift. And the maximum velocity is v max is equal to the amplitude times omega. And here, we can note that the velocity is 0 at max displacement. And we also know that the velocity is max at the equilibrium. Now for acceleration, we have a of t is equal to negative amplitude omega squared times cosine of omega t plus the phase shift. And the key simple harmonic motion defining relationship is a is equal to negative omega squared times x. So here we know that acceleration is always directed toward equilibrium. And also we know that acceleration is proportional to displacement. Some phase relationships that you should know are that the position is going to be your reference, the velocity is going to be shifted 90 degrees, and the acceleration is going to be shifted 180 degrees. So some graphs that you have to recognize are going to be the position versus time, which is, you can draw here, sinusoidal, and the period is equal to the time between the peaks, and the amplitude is equal to the vertical height. The velocity versus time, which is sinusoidal and is shifted 90 degrees from the position time graph, and the acceleration versus time, which is sinusoidal again, and it's also inverted relative to the position graph. Now we can start with some examples. So let's say we have a particle moves according to x of t is equal to 0.2 cosine 4t. So we want to find the amplitude, the angular frequency, the maximum velocity, and the maximum acceleration. So the amplitude is going to equal to 0.20 meters. The angular frequency is going to be equal to 4 rad per second. So this comes from here. You're just identifying where these things are in the relationship. And the maximum velocity, v max, is equal to the formula the amplitude times omega. And we can see those that we previously identified are 0.20 times 4, and that's going to be 0.80 meters per second. Now, the max acceleration is going to be your amplitude times omega squared, which is 0.20 times 16, which is equal to 3.2 meters per second squared. Now, an acceleration versus position graph has a slope of negative 25 seconds to the power of negative 2. Find the angular frequency and the period. So we know that a is equal to negative omega squared times x. Therefore, we know that we can write that we can rearrange this as omega squared is equal to 25, And from that, we can take the root of both sides, and we have omega is equal to 5. Now for period, we know the period is 2 pi over omega. So then we can write that as 2 pi over 5, and that's approximately 1.26 seconds. Phase reasoning. At a certain instant, a simple harmonic motion mass has a positive position, 0 velocity, and what we want to do is determine the direction of acceleration. So we know from a is equal to negative omega squared x that you have a positive x. That means that the acceleration is negative. So the acceleration points toward the equilibrium. Now, we can continue on with our next question. A mass spring system undergoes ideal simple harmonic motion. The graph of the kinetic energy versus time shows a maximum value of 4.0 joules. What is the total maximum energy of the system, and at what points is the kinetic energy equal to 2 joules? So in ideal simple harmonic motion, we have that the total is going to be equal to the kinetic energy max, and the E total, that is going to be equal to 4.0 joules. At what points is the kinetic energy equal to 2 joules? Well, we know that the kinetic energy is equal to the total energy minus the potential energy. Therefore, the potential energy is equal to the total energy minus the kinetic energy. And plugging in our values, that's going to be 4.0 minus 2.0 is equal to 2.0 joules. Now, finding the spring potential energy, that's going to be U is equal to 1/2 kx squared. So when U is equal to 2.0 joules, the object is between the equilibrium and turning points at 2 positions. And those positions are x is equal to plus or minus x. Now, examining the acceleration position graph, a graph of acceleration versus position is a straight line through the origin with a slope of negative 36 seconds to the power of negative 2. Show that the motion is simple harmonic motion. So, the condition is the acceleration is equal to negative omega squared times x. And we know that the slope is omega squared is equal to 36. So rooting both sides, we have omega is just equal to 6 rad per second. Therefore, it's simple harmonic motion. To find the period, t is equal to 2 pi over omega. That's just 2 pi over 6. That's equal to pi over 3. So that's approximately 1.05 seconds. At a certain instant, a mass in simple harmonic motion has 0 velocity, max acceleration. Determine the position of the mass and the direction of the acceleration. So the velocity equals 0 at x is equal to plus or minus a, and the acceleration a is equal to negative omega squared x. So at x is equal to plus or minus a, the acceleration has max magnitude and points toward the equilibrium. A spring mass system has total energy E, and the potential energy at displacement x is equal to 0.3 meters is 3 joules. Find the kinetic energy at that position. So to do this, we know that kinetic energy is equal to E minus U. Now, if E is equal to 5.0 joules, K is equal to 5.0 minus 3.0, which is equal to 2.0 joules. Kinetic energy is max when U is equal to 0. So that means that X is equal to 0 at equilibrium. A particle moves according to x of t is equal to 0.5 cosine 10 times t. Find the amplitude, angular frequency, omega. A mass in simple harmonic motion has the total energy E. Compare the kinetic energy when x is equal to a over 2 versus x is equal to the root 3 times a over 2. Potential energy in general is U is equal to 1/2 kx squared. So at x is equal to a over 2, so this is going to equal to 1 over 4e. So rearranging this, we have k is equal to 3 over 4e. We have u is equal to 3 over 8ka squared. That's going to equal to 3 over 4e. So then we have k is equal to 1 over 4e. What graph corresponds to acceleration versus time? Because acceleration is negative omega squared times x, and acceleration is sinusoidal and 180 degrees out of phase position. A system's total mechanical energy decreases steadily over time. Can the motion still be simple harmonic motion? Ideal simple harmonic motion has the requirement E total is constant, and a decreasing energy means that you have a non-conservative force present, and that means that the motion is not simple harmonic motion. A particle undergoes simple harmonic motion described by x of t is equal to 0.3 cosine 6t plus pi over 3. Now starting off with the amplitude, a is equal to 0.30 meters. Omega is equal to 6 radian per second. Period is equal to 2 pi over omega, 2 pi over 6, pi over 3 seconds. The max speed, that's going to be amplitude times omega, which is 0.3 times 6, which is equal to 1.8 meters per second. A max is going to be A times omega squared, which is equal to 0.30 times 36 is equal to 10.8 meters per second squared. A velocity time graph for a mass in simple harmonic motion is sinusoidal with a max speed of 2 meters per second and a period of 1.6 seconds. Find the angular frequency. So we know that A max is equal to the amplitude times omega squared. So that means omega squared is equal to A max over A. That's going to be 5.0 over 0.25 is equal to 20. Now that means omega is equal to the root of 20, which is approximately 4.47 rad per second. The amplitude, the amplitude of motion, this is actually, hold on. This is one lower. So we can actually continue on with this. A velocity time graph for a mass in simple harmonic motion is sinusoidal with a max speed of 2 meters per second and a period of 1.6. Find the angular frequency. So the angular frequency is going to be omega is equal to 2 pi over t, 2 pi over 1.6, 3.93 rads per second. Now for the amplitude of the motion, we know V max is equal to the amplitude times omega. The amplitude is equal to V max over omega. That's going to be 2.0 over 3.93. That's approximately 0.51 meters. An acceleration time graph for a mass in simple harmonic motion has a maximum magnitude of 5 meters per second squared. The amplitude of the motion is 0.25 meters. Find the angular frequency. So we can use that the A max, the maximum acceleration, is equal to the amplitude times omega squared. Rearranging for omega squared, we have omega squared is equal to A max divided by the amplitude, which is 5 over 0.25, which is 20. Now rooting both sides, we have 4.47 radians per second. Now for the period, t is equal to 2 pi over omega, 2 pi over 4.47, approximately 1.41 seconds. At a certain instant, a mass in simple harmonic motion has a negative displacement and positive velocity. So we first want to determine the acceleration direction. A is equal to negative omega squared x. Negative x is a positive acceleration, whether the mass is moving toward or away from the equilibrium. A mass spring system has total energy E at a certain point. The displacement is equal to x is equal to 0.6 A. Find the fraction of total energy that is kinetic energy. student measures acceleration position from a moving object and finds out the acceleration is always proportional to the displacement and opposite in the direction. Explain why this motion is simple harmonic motion and identify the graph that confirms this. Simple harmonic motion is a is equal to negative omega squared. And then the graph is acceleration a particle's acceleration is given by a of t is equal to negative 9 cosine 3t. Show the motion that is simple harmonic motion. Find the position function. Two systems have identical amplitudes and spring constants. System A has twice the mass of system B. Compare their periods and their max kinetic energies. So T is equal to